Very good. So let's look at now G.I. Taylor's famous interference experiment. So this experiment was carried out in about 1909. And the basic idea here is that it is a standard sort of light interference experiment. So we're going to have some source of light over here, but one key aspect of this is that it's going to be a rather dim source for our light. Then we're going to send it through a blocking plate with two finite slits in it, say. So a blocking plate with, say, two slits. So it's kind of going to be a very standard kind of two-slit experiment. And then, of course, we're going to record the intensity or the pattern of light on the other side with some kind of a photographic plate, a photoplate. Now, this photoplate it's important for us to understand a little bit how the image is actually recorded. Photography in the old days with film was actually a rather interesting process. So basically what would happen would be inside, or coating on the paper, depending on how it's done, there would be these very tiny silver halide crystals. Crystals of, say, silver, Ag, right, silver chloride. Now, silver chloride actually is transparent. But what would happen is when a light would come on in, now we know one of these energy packets get delivered that will actually move the electrons around in here and break some of these bonds so that the silver will precipitate or come out of that little solution that we have here, or its compound. And when it does that, it leaves behind a little black spot, and that's how the image is actually recorded. You could alternately imagine instead of that, maybe this plate consists of, say, photoreceptors, such as in your eye, the rods and cones photoreceptors, right, which would then be making up the image or kind of counting how many packets get delivered in different locations. And finally, if you really wanted to do this in an exotic way, you could combine with previous experiments. You could do this in a cathode ray tube and do it by cathode rays. And simply look for the events of the arrival of these photons by wherever, say, an electron then would jump out of your photoplate and make it into a cathode. Now, here's what happens when you do the experiment. So we have this experiment. We kind of tune this source down so that the arrival rate of the packets is fairly low, and we let them begin arriving, and at some point you will have your first event, right? Your first delivery of one of these packets of energy. We don't know where it will be. Maybe it's going to be up here. And then the next one comes, and again, we don't know exactly where it might be. It might land down here, and then maybe another one. Maybe it lands more in the center, right? But they have to land somewhere because they are these discrete packets. Now, as time goes on, some kind of pattern will begin to build up. And let's suppose, say, I get now in my next event, it ends up maybe rather close to this one. So just for my sketch, I'm going to make this like into a little histogram. So we can imagine sort of binning our experiment into different bins. And now that maybe two events have happened near the same spot, I will sketch it this way. So as time goes on, of course, what's going to happen is I'm going to build up some kind of pattern. Again, these all arrive randomly in different locations at different rates. As you might expect, the middle is a little bit more popular. So maybe I get a few more here in the middle, maybe another one over here or another one over here. And eventually then what begins to happen is you build up then a nice pattern, which of course corresponds to this finite two-slit interference pattern that you guys are experts at computing, say, from physics 22.14 or from physics 22.18, your standards kind of wave course on waves. So that's the basic observation here. Now this does have some pretty profound consequences, so I'd like to sketch out some of the lessons of this. Now the first lesson is really a little bit of a more of a background or a perspective on how I would like us to think about this. So it's really more background. What I'd like you to notice is that this process that I've described happening here, which is really what we're forced into concluding of what must be happening, it comes about because of this fundamental discreteness, right? We can't kind of build up this image just all at once continuously. The packets have to land somewhere. And that's very, very different about how we normally think about the world around us. So I want to give you sort of a caveat or a warning as we begin to think about this new kind of world where we look at the world at this very fine scale. And that is the following, is that the microscopic world, and I'm going to define microscopic very specifically, and that's when we begin looking down in such detail that the quantities that we're dealing with are comparable to this fundamental discreteness that is described by Planck's constant h, that this microscopic world behaves very differently from the macroscopic world that we're used to, the world of our common sense, right? Because these packets really are very tiny. So macroscopic, which we would define, is where we're talking about things that are much bigger than Planck's constant world. So I want us to really focus on this idea and get it into our heads, right? That all of your intuition and common sense and all the physics that you've studied so far is always occurring in a regime where these individual packets are really very, very tiny. And because they are so tiny, we can really think of, for example, like a particle as sitting at some location and kind of continuously moving around in space. Or we can think of this pattern as starting small and then just kind of continuously building up. But the real world isn't that way. We have these discrete packets. So you shouldn't be surprised that your common sense isn't going to really work down on this microscopic level. So that means we really need to set aside our prejudices and begin to just take an open-minded look and accept the world for what it is based on the actual experimental evidence, right? That is our job here, really, as scientists. And what the evidence is really telling us now are some very interesting and somewhat different things. So here's the first thing I'd like you to notice, is that the delivery of these packets make up these very discrete microscopic events. So microscopic events, rather than being continuous, are discrete. And this is very important. We can't tell where they are going to happen. And they occur at fully random locations. Let's call the location where such an event happens X. Right? And one way we know this is that if we look at our histogram as it builds up, right, we are basically doing a counting experiment, right? And our counting experiment, you can verify here, it actually obeys perfect counting statistics. Now, the statistics of counting that we talked about last time, I forget whether or not I'd given you the official technical name for that kind of statistics. It's called Poisson statistics because the distribution that they follow is known as something called the Poisson distribution, but they obey perfect Poisson statistics. So what this tells us, this is very strong evidence that these are truly, the arrivals are truly random arrivals that are uncorrelated with each other and random. Now that's quite a different way of thinking about the world as having all these random events going on. We're not used to that, but that's because we're used to things varying continuously. But when you combine the fact that we have to build up a certain pattern, but we have to build it from discrete events, you begin to see that the particular location of any one given event, it's got to select something that reproduces that property that it finally builds up, and so the locations are going to be random. But fortunately for us, it's not complete chaos, right? It's not that we can't say anything about what's going to happen in the world around us. We can't say where things are going to happen, microscopic, but what we can say is something about the probability distribution. We can predict the probability distribution, the probabilities, and I'll call those P of X, And in fact, here I can give you the precise mathematical description for calculating this probability, because we know in the end they have to build up the brightness pattern that we're expecting from our 2214 or 2218. So we know how to predict those. Those are going to be just proportional to the brightness that we would calculate using, right, the basic rules, the interference rules from your more basic wave on course, from your interference rules from, phys, maybe, depending which course you might have taken here at Cornell. It could have been 2214 or your 2218. And the beauty is you guys already know how to do these computations. So you already know how to calculate, for at least photons, this probability distribution and everything that there is to know about these types of events. My next lesson that I'd like to point out to you from this, really more of an observation. So let me make this more one of my observations here with a bullet. The next observation I'd like to make from this is that item 1, actually, and item 2, if you can really get your mind around them, is the entire content of quantum mechanics. That's what we're going to be doing this semester, is learning how to calculate these probabilities of where these events are going to occur, because that's really what there is out there for us to be able to predict. So 1 and 2, if you can really understand them, you understand this entire course. 1 and 2 are the heart of the quantum theory, or heart of quantum mechanics. Now, the last point I would like to draw out of this is something we always have to keep in mind. Of course, we are building a new theory, right, about the world around us based on some new empirical evidence, some new data. And we've built up a theory now, right, that can describe, right, the behavior of these new phenomena. But a new theory in science, of course, if it's going to supersede a preceding theory, not only has to explain all of the new evidence that the old theory could not account for, it also has to be able to explain all of the old evidence that the previous theory did completely account for. And that has a special name when you apply that in quantum mechanics. That's called the so-called correspondence principle. Correspondence principle. And what the correspondence principle says is that when we go, the quantum mechanic predictions, QM predictions, must match the so-called classical predictions. We have to reproduce those, and those are what we call those classical predictions, or really the term I would prefer to use are the from what we experience in our normal macroscopic physics, which is frequently called classical physics, right? Must match the classical predictions when the objects, right, are large. Again, when we go to a regime where things are much, much larger than h, right? That's just simply saying we had to reproduce the preceding theory, but it turns out this puts some very powerful constraints and gives us a very close guide, as you will see, in how we're going to now synthetically construct a theory that can account for all of our evidence, including all of the good classical physics that you've already learned. Now, associated with this, there's another concept which can kind of make this more mathematically formal. This is something called the classical limit. And the classical limit is a formal mathematical way of quantifying the correspondence principle, is that we have to get classical physics, so the classical result. So if you calculate something in quantum mechanics, right, it has to recover the classical result when things are very large, or a mathematical way of saying that is, formally speaking, when you take the limit you take the limit of any expression that you derive. When you take the limit, that h, Planck's constant, then goes to 0. Very good. So these are really a whole set of very important, key, critical lessons that we learn directly from this G.I. Taylor experiment.